In this video, we are going to review some properties of our Arabic number system, and then we're also going to use this to motivate different number systems, and we're going to learn how to go back and forth and do computations in various number systems. Now, our number system is what's called a base 10 number system or a decimal number system, and the numerals that we use are called Arabic numerals, as shown down here on the bottom point of this slide. But the idea here is that the number 10, stressed in the base 10 number system, and every now and again 5, is really integral to the way that we count and the way that we group things. This is mostly because we have 5 fingers on each hand and 10 fingers total on our hands. And so you can see this in the way that we assign denominations to money. 1 dime is 10 pennies, or $1 is 10 dimes, or 10 times 10 pennies. The metric system is very focused on the number 10, and almost all countries in the world agree that that somehow makes the metric system better. And various different number systems throughout time have also stressed the importance of the numbers 5 and 10. So the Romans are sort of our first canonical example, or perhaps the one that people are most familiar with, but also Chinese and Hebrew numerals have focused on creating number systems that really revolve around the number 10 and occasionally 5. This isn't true of all different languages and all different number systems, but these classical ones have this property. But every now and again you find something different, and I feel very strongly that if cartoon characters developed their own number system and were doing things truly accurately, that they would not focus on the number 10 at all. They would focus on the number 8 as being incredibly important to them. And this is because, for whatever reason, when you draw cartoon characters, you give them 4 fingers on each hand and 8 fingers total. So if cartoon characters were to develop their own number system, I believe that they would use a base 8 number system, and that 8 would be of vital importance to cartoon characters. A base 8 number system, sometimes called an octal number system, would put all of the importance on the number 8 and in grouping things in 8s and powers of 8s as opposed to 10s and powers of 10s, the way that we do things. So if you think way back to when you were learning about numbers, you often talked about place value. And we have places for ones and tens and hundreds and thousands. And to stress the relationship those numbers have with the number 10, we say ones, tens, 10 times tens, 10 times 10 times tens, and so on and so forth. Cartoon characters, if they were to develop the same type of number system, or this base 8 or octal number system, would have place values for ones, but then for 8s, and for the 8 times 8s, and the 8 times 8 times 8s, and so on and so forth. As an example, let's consider the number 532 as a decimal number. We think of 532 in the following way. We think of that as 500 plus 30 plus 2. Or written differently, we think of that as 5 times 10 times 10 plus 3 times 10 plus 2 times 10 to the 0th power, which would be our ones value. And that's where that 532 comes from. If there were what we call 532 things sitting out, a cartoon character would not group that according to hundreds and tens and then leftover ones. A cartoon character would take that number 532 and break it up according to powers of 8s. So it just so happens that 8 cubed is 512. So a cartoon character would take 512 of those things and think of that as one group of 8 cubed. After taking away that 512 pieces, there'd be 20 things left over, so that's no copies of 8 times 8, no copies of 64 there. But there are 2 groups of 8 left over in those 20 things, and so they would group the remaining 20 things in 2 groups of 8, and then the 4 would be left over. And so a cartoon character would refer to that same number of objects that we call 532. A cartoon character would feel much more comfortable thinking of that object as 1024. Now, this can get very confusing, and so to avoid confusion, we're going to put the base of the number system as a subscript next to the number in parentheses. So we'll write 1024, we'll throw a parentheses around that and then put a subscript 8 in order to indicate that that 1024 is being thought of as a base 8 number. So that would stress that that's really our number 532 and a cartoon 1024. Coincidentally, if a cartoon character we're talking about 532, so if we were thinking about 532 base 8, then what that would mean is we have 5 copies of 8 squared, 3 copies of 8 to the first power, and 2 things left over. So if you do the arithmetic on that, 5 times 8 squared gives us the 320, 3 times 8 gives us the 24, and the 2 left over. 2 times 8 to the 0 gives us the 2. That we would represent that quantity of things as 346 in a decimal number system. As I mentioned before, there are various other cultures that have used different number systems than what we use. So if you are not looking at the metric system, but you're rather focusing on feet and inches and things like dozens, you can see that we use something of a base 12 number system. Here 12 is very important to us, and grouping things into 12s is the way that we like to do things. 12 inches per foot, 12 eggs in a dozen. The Mayans used a base 20 number system, presumably because we have 10 fingers and 10 toes, and altogether you have 20 things that you could count on using the digits of your body. If anyone's ever learned French, or if anyone is familiar with Welsh or the Yoruba language, then you'll know that these languages use somewhat variants of a base 20 system. In French, you count up to 79 by itself, and then 80 becomes 4 copies of 20. So in some sense, we view this 20 as 80 doesn't get its own number. We view this 20, this 4 groupings of 20, as more important than giving its own number to 80. But other periods throughout history have had different number systems. There are a handful of tribes in New Guinea that use number systems with base 6 or base 27. Other than sort of historical or cultural examples, people often use computers and computer programming as a good motivation for studying other number systems. So internally, computers only use zeros and ones, and so they use what's called a binary number system or base 2 number system. Computer programmers tend to use a slightly larger but related number system. They use a hexadecimal number system, which is a base 16 number system. And we'll see a little bit of why that difference exists in the coming slides. But let's do an example of converting things to binary numbers, since this is so important to modern technology. So let's take the example of 800, our decimal number 800, and we want to figure out how to write that as a binary number. So if you're really good with your powers of 2 because you're a computer programmer, or if you've ever played the game 2048, you're pretty decent at rattling off powers of 2. The first thing we have to do is find the largest power of 2 that is smaller than our target number here, which is 800. So for us, that's 512. If we go up one more, we'll be at 1024, which is too big. It's bigger than 800. So 512, which is 2 to the 9th power, is the largest power of 2, less than 800. So our goal then becomes starting at 512 and looking at all the powers of 2 going down to 1, we want to somehow express 800 as a sum of these numbers. Where all we're allowed to do is fill in zeros and 1 here. Is the number in the sum or is the number not in the sum? So we know that 512 should be in the sum. It's this largest power of 2 without going over 800. So we need to fill in a 1 in the 512 spot. Yes, a copy of 512 is required. Now, after we take away those 512 objects, we have 288 things left. What we need to do now is repeat a similar process and determine if the values 256, 128, and so on and so forth all the way down the line, see if we need copies of those numbers in order to build 288 as a sum of them. So moving on, 288, we do need a copy of 256. We have room for that. So we fill in a 1. Yes, we do need the number 256 in order to do this. And then we take away those 256 things from the 288 things, and we have 32 left over. And we repeat again. Now we determine if the values 128 all the way down through 1 are required to build the what's left, which is 32. Now, 128 and 64, those are too big. They're not required to write 32, and so we put zeros in there. I don't need any copies of 128, and I don't need any copies of 64. Perhaps a better way to say that is I don't have them. I don't have a copy of 128. I don't have a copy of 64. However, I do have a 32. Yes, a copy of 32 is required, and in fact, no other values are required. I have exactly 32 left over. So I do need the 32, but I don't need 16, 8, 4, 2, or 1. There's nothing left over after I take those 32 things away. So if I were to take the decimal number 800 and represent it in binary, I would represent it this way: 11001 and 5 zeros. Now, some observations we can make will bring to light maybe why computers internally use a binary number system, but why we don't use that number system as computer programmers. In general, if you're writing in base n, no individual digit should exceed n. It shouldn't even match n. So for example, when we were using a binary number system, which is a base 2 number system, we only had zeros and ones. When we're using a decimal number system, in any one particular place, we only ever have the numbers 0 through 9. And in an octal system, a base 8 number, we would only have the numbers 0 through 7. No individual digit or place value should exceed or match the base. Now, similarly, think about the last example. In binary, the base 2 is smaller than the base that we started with, which was 10. And what this led to was a number like 800, which is 3 digits when written in decimal. It made this number expand and get a lot bigger. I needed more place values to write the same quantity of things. And so this is because I don't have as much freedom to work with. Each place value cannot hold as many digits as it could previously, and so I need more place values in order to express the same quantity. If we were going to move, as we will in a moment, to a base that's larger than decimal, then we actually need new symbols in order to represent the new numbers traveling up to the base, right, so that we can have them exist in a single digit. We typically use capital letters of the alphabet for this. So as we'll see in a minute when we do a hexadecimal example, we don't regroup yet and move on to the next place at 10. 10 in a decimal number system means 1 copy of 10 and 0 single things. But 10 doesn't get sort of regrouped yet if we were at 16, and so we need a new symbol to represent 10 that can just sit there in one place value. And so what we do is we start by saying 10 is A and 11 is B, and so on and so forth until we hit the number 16. Now, going back to what we started talking about at the beginning of this slide, decimal numbers represented in base n, if we had chosen the n to be larger than our 10, they should somehow shrink, either taking up fewer place values or maybe taking up the same number of place values, but using smaller leading numbers in that sense. So here's our example. Let's do the same number, 800, but expressed as a hexadecimal number. Now we start this process over again, but 16 is important to us instead of 2. So we're going to look for the largest power of 16 that is going to be smaller than 800, and for us that's 256, or 16 squared. Now our goal is to only fill in a much fewer number of digits. We have a 256 place, a 16's place, and a 1's place. And inside each place value, we're either going to use the numbers 0 through 9, or when we hit 10, 11, 12, 13, 14, 15, which are all perfectly acceptable for a single digit here, we need a method of expressing them as to not get confused. So we'll call A10, B11, and so on and so forth up until F, which would represent the number 15. With our 800 example, we see that we need 3 copies of the number 256 to get 768. That's the largest multiple of 256 that's less than 800. So what we're going to do is say I need 3 copies of 256, and then I'll have 768 things. So I put the 3 here, and then I determine what's my leftover. 800 minus those 3 copies of 256 things is 32 left over. And just like I did with binary, I now determine how the values 16 and 1 are required to build 32. Do I need 16s? If so, how many? Do I need 1s? If so, how many? Now, 2 times 16 happens to hit 32 exactly. The largest multiple of 16, less than or equal to 32. So I need 2 copies of 16 and 3 copies of 256, and if I combine those things, I'll end up with my number 800. Since I hit 32 exactly on the nose with these copies of 16, there isn't anything left, so the value 1 is not required in order to build what's left when this is done. So I don't need any copies of 1. Put a 0 there, and I'm left with 800 being represented as 320 in base 16. So it didn't happen to be the case with this example that I needed fewer digits. I still needed 3 digits, but 320 is a number that would typically be less than 800 if they were both written in decimal. So the number shrank in a sense. Last but not least, I do want to show you how to do one computational example of doing arithmetic with different number systems. So let's suppose that we wanted to take A6, which is a perfectly good hexadecimal number, and add it to this other hexadecimal number, F5. One way to do this, the way that people often feel the most comfortable, is to take the numbers A6 and F5 and to convert them back to decimal numbers. Once they're decimal numbers, we feel very comfortable doing an addition, and then after the addition is done, we could then go through this process that we've done examples of before to convert back to a hexadecimal value. However, I'd like to point out and do an example showing you that there's another way that doesn't require you translating back to what's comfortable for you at all. It doesn't require you translating back to decimal and then back again to hexadecimal. This method keeps everything the way that it is, but thinks about what the base 16 really means. The base of the number system is telling us when it becomes important to regroup things. It's telling us that I can have anywhere from 0 to 15 of a particular quantity, but as soon as I reach 16 of that quantity, I can kind of regroup that 16 as one more of the next value and keep what's left over in this particular spot. So let's demonstrate that with an example. This same example, A6 base 16 plus F5 base 16. The first thing I'm going to do is I'm going to focus on my ones place, much like I would in a standard addition algorithm. And I'm going to say I have 6 ones and I have 5 ones. So altogether, I have 11 ones. In a decimal number system, 11 is too big, and so I would need to do a regrouping process here. I'd keep 1, and I'd take 10 of them and sort of regroup and say, okay, now I have 1 copy of 10 with 1 thing left over. But 10 is not important to us anymore. 16 is the number that's important to us because we're working in base 16. So 11 is smaller than 16, and I don't have to do any regrouping here. The only thing I need to do is know how to represent the number 11 with a single symbol, and that symbol happens to be B. At this point, I'm entirely done adding in the ones column, and I didn't require a carry, so I move right over into the 16s column. Say, okay, I want to add A plus F. However, I need to know what the A stands for, or what that means when I write it in base 16, and similarly for the F. So the A means that I have 10 things, and the F means that I have 15 things. So in terms of whatever I have 10 plus 15 of them. I have 25 objects in this column. Now 25 is a number that's bigger than 16. So what I want to do is take 16 of those 25 objects and regroup them. And when that's done, so 16 of those 25 objects will give me one of a larger place value, and then there are 9 things left over of this same place value. So what I do is I say I have 9 things of this place value, and I sort of carry the 1, much like I would in a standard arithmetic algorithm. So I have 9 copies of this place value, and I had enough to trade in for 1 more of the next denomination. And you bring the 1 down and say A6 plus F5 in base 16 is 19B in base 16. No translating back and forth the decimal required. In summary, after watching this video, I hope that you will be able to translate numbers between different base systems, mostly from decimal into other number systems, but there's just one additional step needed if you want to translate from binary to hexadecimal, for example. I'd also like you to understand how changing the base of a number is either going to expand or shrink the number of digits used to express that number. So if you're going from a decimal system to, say, a hexadecimal system, what's going to happen to the number? Will it get bigger or smaller? If you're going from a decimal system to a binary system, what's going to happen to the number? Will it get bigger or smaller? And last but not least, I'd like you to have just the beginning ideas of how to perform basic arithmetic computations on numbers when they happen to stay in a different number system.